this is Lemis Dengir from Knowledge and Skills, and today we are going to talk about non-traditional machining processes. Chemical machining is the process of removal of material from the workpiece using chemical reactions by immersing the workpiece into a chemical solution. Chemical machining is a process used for metal removal purpose by dissolution in a controlled manner from the workpiece by the application of acidic or alkaline solution, and the solution is called the etchant. Chemical machining process is widely used to produce microcomponents for various industrial applications like micro-electrochemical systems called MEMS and semiconductor industries. As the name suggests, chemical machining employs an appropriate chemical solution to etch away material from work surface. Such chemical solution is called the etchant and is highly corrosive. No separate cutting tool, shaper tool, or similar device is used here, and the etchant itself reacts with work material, and thus the latter one gets dissolved into the etchant solution. Thus, it's mandatory to select etchant composition based on the work material, and its process is independent of mechanical, electrical, or thermal properties of the material. However, it relies on its chemical reactivity. There are two substances mainly used in this machining process, which are the maskant, as we see here, and the etchant itself. First of all, about the maskant, it is a chemical-resistant coating that is used to cover the surfaces which are not to be machined. So the maskant do not allow etchant to penetrate through it and reach the material which is not to be dissolved. This technique is very useful to produce complex configuration in delicate parts which cannot be done by the conventional machining processes. Then the etchant is the chemical solution used in this process which dissolves the workpiece and removes material by a chemical reaction. To avoid uneven material removal from the workpiece, fresh etchant is continuously sprayed on the workpiece or it's submerged in the etchant tank. To increase the material removal rate, the etchant is agitated and, if necessary, the etchant is heated. The strength of the etchant can be maintained by proper filtration, addition of new chemicals, replace some percentage of used etchant by fresh one regularly, and so on. There are different etchants used in the market to machine different materials. And we can cite, for example, FeCl3, which is used for aluminum, copper, nickel, and their alloys. FeNO3 for silver, HF for titanium, HMO for tool steel. Apart from these, other etchants are used like chromic acid and ammonium persulfate. The third method concerns the photoresist maskant. And it's exclusively used in photochemical machining. So this technique has become very common nowadays, and it's used to produce complicated but accurate shapes. Here in this video we will see a demonstration of the different steps used in this method. So the workpiece is coated with a photoresist material, and a master transparency is held against the workpiece, and it's exposed to ultraviolet rays. Then, after that light activates the photoresist material in those areas corresponding to opaque parts. And the third step is using this technique, a tolerance of 25 to 5 micrometers can be produced, so it's really very accurate. Now let's discover the electrochemical machining process and how it works. So, ECM is a way of machining a part without actually having any contact between the tool and the workpiece. The workpiece is charged positively, as you can see, and the tool is charged negatively, and between the two pieces there is a tiny gap where they don't actually touch, but there is an electrolyte fluid between the two that slowly removes atoms. And as the tool is slowly moved down towards the workpiece, more and more atoms are removed until the workpiece conforms to the same shape as the tool. This is convenient because there is no actual contact, so there is no tool wear and no friction, which causes heat. This can be used for a variety of parts and many complicated shapes, and it can also be used for tiny parts. So, how does electrochemical machining work? To sum up, in electrochemical machining, material is removed by ionic dissolution but under the assistance of electrochemical reaction. No corrosive etchant is used here. Instead, a suitable electrolyte is employed. ECM requires a shaped tool made of electrically conductive material that is placed close to the workpiece. A small gap is maintained. Both tool and workpiece are connected with two polarities of a DC power source and are immersed partially into the electrolyte. Under the presence of sufficient potential difference, electrochemical reaction initiates following the principles of Faraday's law. Here, the tool material and the electrolyte are chosen in such a way that material from work surface only gets dissolved into the electrolyte. Tool and electrolyte remains intact. The ECM tool must have profile based on intended profile because inverse shape of the tool is imparted on the workpiece. Moreover, ECM can be applied for electrically conductive material only. Various similarities and differences between chemical machining and electrochemical machining can be cited. So, for example, as a similarity, both chemical and electrochemical are considered as advanced manufacturing processes. However, none of them is hybrid process, and none of them causes burr or thermal damage to the machine surface. Both processes are quiet, no noise, and both processes are independent of the mechanical properties of the work material. Thus, ductility, hardness, strength, and so on don't possess any limitation of the application of both of them, and both offer similar levels of surface finish, about between 0.1 and 2 microns. However, there are several differences between the chemical machining and the electrochemical processes. First of all, in chemical process, as its name suggests, the chemical machining is one chemical energy-based NTM process. However, ECM is one electrical energy-based NTM process. The second point is in chemical machining, here the material is removed in ionic form due to controlled dissolution by chemical etchant. The etchant slowly dissolves the metal to realize machining. However, in ECM, here also the material is removed in ionic form, but due to controlled electrochemical dissolution of the work material. The third point is in chemical machining, it's independent of electrical conductivity of the workpiece metal, so it can be applied for conductive and non-conductive materials. But ECM it's applied only to electrically conductive workpieces, as it's used as the workpiece is used as anode of the electrolytic cell. The fourth point is that in chemical machining, no additional electrode is necessary as the chemical reaction takes place between the etchant and the workpiece. And in ECM, an electrode having curvature according to intended shape is absolutely required to complete the electrical circuits. Next, regarding the differences, in chemical machining, no power supply is necessary as the process is not related to electrical energy. But in ECM, one DC power supply is required to maintain desired potential difference between the cathode, the tool electrode, and the anode, the workpiece. Next, in chemical machining, here, suitable etchant based on workpiece material is employed, and typical etchant include FeCl3, CuCl3, FeNO3, HNO3, and HF. And in ECM, instead of the etchant, appropriate electrolyte is applied in ECM, and typically electrolyte includes NaCl and NaNO3. Then, in chemical machining, the rate of chemical dissolution is very hard to control. Once the process is initiated, the rate cannot be controlled accurately anymore. But in ECM, the rate of electrochemical dissolution can be controlled during the machining simply by adjusting the inter-electrode gap and the current. Then, in chemical machining, it cannot inherently control the area from where the material should be dissolved. The material is removed wherever the work surface is exposed to the etchant, of course, and thus the mask can be separately applied to control the exposure. In ECM, it can be controlled. The process can inherently control the area from where the material should be removed. The dissolution occurs only from the areas where tool is in close proximity. And finally, in chemical machining, chemical etchants are highly corrosive, and thus the process possesses a risk to the operator. Nevertheless, in ECM, the etchant is not such corrosive, and thus the process is somewhat risk-free towards the operator. There are several non-traditional machining processes using the mechanical energy, and we call them the mechanical NTM processes. Among them, we find abrasive flow machining, ultrasound machining, waterjet machining, and abrasive jet machining. The abrasive flow machining, also known as abrasive flow deburring or extrude honing, is an interior surface finishing process characterized by flowing an abrasive-laden fluid through a workpiece. This fluid is typically very viscous, having the consistency of putty or duff. AFM smooths and finishes rough surfaces and is typically used to remove burrs, polish surfaces, form radii, and even remove material. In abrasive flow machining, the abrasive fluid flows through the workpiece, effectively performing erosion. Abrasive particles in the fluid contact raised features on the surface of the workpiece and remove them. The fluid is forced through the workpiece by a hydraulic ram. Let's have a closer look. An abrasive flow machine normally includes two medium chambers equipped with hydraulic rams, a fixture for holding the workpiece, and a clamping system that holds all the components tightly together. Most machines allow for the loading of different types of abrasive medium and include the capacity to adjust the pressure used in extruding the medium through the workpiece. They may be manually operated or automated using CNC. In waterjet machining, clean water is pumped to a high pressure between 2,500 and 4,000 bars with the help of intensifiers, and the pressurized water is delivered to the work surface in the form of a jet using a small diameter nozzle. The nozzle converts the pressure energy of the water into the kinetic energy, and thus high velocity 1000 meters per second jet is obtained. Apart from delivering the water jet, the nozzle also maintains the desired delivery angle and nozzle tip distance, called NTD. In order to avoid flaring of the water jet after discharge from the nozzle, suitable stabilizer is sometimes mixed with the water. In waterjet machining, the high-velocity water jet erodes the material from the workpiece. It's suitable for cutting leather, textile materials, food polymer, etc. However, the water jet does not possess enough power to slice metallic or ceramic objects. To improve the jet power, suitable abrasive like alumina, olivine, garnet, etc. can also be mixed with the water, and such a process where abrasive particles are mixed with highly pressurized water before delivering onto the work surface is called abrasive water jet machining, AWJM. Here, water is used to entrain the abrasives and to flush away eroded materials. Water does not directly participate in micro-cutting of the material, and the abrasives only erode the material. So how it works? We have a pipe connected with a control valve from which a high pressure water will come, and at the other end of the pipe a nozzle is connected for converting the energy of the liquid or enhancing the energy, the kinetic energy of the water or the liquid. And also in this, an abrasive feed is engaged between the water jet and the abrasive jet. The abrasive particle and water will mix and then will work together for metal removal in this process. This is the abrasive tube. Clear water and abrasive slur will mix in the efficient manner, and then they will be pushed to the workpiece. Now we see the working of the abrasive jet machining as soon as a high pressure water comes from the control valve and moves through the pipe. The water reaches the nozzle, and due to the nozzle's small dimension, it converts the energy of the liquid into high kinetic energy, and suddenly abrasive feed is given to this water jet, and mixing together they strike on the workpiece and remove the metal. There are various similarities and differences between the waterjet machining and the abrasive waterjet machining. Let's see now the differences between both processes. In waterjet machining, a high-velocity jet of pure water, sometimes mixed with stabilizer, is used to erode the material, but in abrasive waterjet machining, a high velocity of a jet of water abrasive mixture is used to erode the workpiece material. Then, in waterjet machining, material removal from the workpiece takes place only due to the erosive action of water jets, but in abrasive waterjet machining, the material removal takes place due to the micro-cutting action of abrasives. Water does not directly participate in cutting of the material. After that, in waterjet machining, no mixing chamber is desired as abrasive is not mixed with water. Nevertheless, in abrasive waterjet machining, a mixing chamber focused tube is required for mixing abrasives with the pressurized water, maintaining the predefined mixing ratio. After that, in waterjet machining, the jet of water does not possess high power and thus it cannot be advantageously applied for cutting metals, alloys, and ceramics. But abrasive waterjet machining, the jet of abrasive water mixture possesses enough power to slice metallic plates of thickness up to 10 millimeters. Next, no cost of abrasive is associated with waterjet machining process, but cost of abrasive is an additional expenditure in abrasive waterjet machining process. After that, the waterjet machining is free from the risk of abrasive embedment on the finished surface. But in abrasive waterjet machining, it is associated with the risk of abrasive embedment, particularly for ductile workpiece materials. Next, in waterjet machining, it's suitable for cutting softer materials like wood, leather, polymer, and food items. It's also used for cleaning and removing coatings. But abrasive waterjet machining can be used for a wide variety of applications, from wood and polymer to metal cutting industries. Finally, abrasive waterjet can be employed in food industries for slicing food items like frozen meat and fish, etc. But the presence of abrasive particles makes the abrasive waterjet machining process not hygienic for applications in food industry. And what about abrasive jet machining? In abrasive jet machining, AGM, a high-velocity jet of abrasive particles accelerated in pressurized air, carrier gas, is made to strike the work surface. A nozzle is used to direct this jet towards the work surface, maintaining predefined standoff distance and inclination angle. When abrasive particles twunk the work surface at high velocity, they remove material by micro-cutting, impact erosion. Abrasive jet machining is commonly used for surface cleaning, such as removing oxide layers, smears, coating, or color present of solid surface. It can also be used for deburring and engraving hard brittle materials. Several process parameters of abrasive jet machining process can be controlled precisely to obtain desired result in terms of dimensional accuracy, material removal rate, and surface roughness. Typical process parameters include carrier gas pressure, flow rate of abrasive particle size, mixing ratio, nozzle diameter, SOD, and inclination angle. Another similar age-old technique is sandblasting, where fine sand particles are propelled to the work surface by pressurized air at very high velocity to remove the material. Mechanism of material removal or impact erosion is the same for both abrasive jet machining and sandblasting processes. However, process parameters of sandblasting cannot be controlled so precisely, and thus it's less reliable for microcutting. It's suitable for cheaper cleaning purposes, particularly in civil applications. Sometimes it's also used to make substrate surface rough before carrying out coating operations. A rough surface can hold the coating layer tightly. Concerning the differences, in abrasive jet machining, several abrasive particles such as silicon carbide, alumina, glass grades, etc. are used to remove material by impact erosion. In sandblasting, only silica and grains, SeO2, are used to remove material by impact erosion. In abrasive jet machining, size of the abrasive particles and its flow rate are more or less uniform, but in sandblasting, sand particles usually have wide range of diameters. Its flow rate is also not uniform in all the cases. Then, in abrasive jet machining, process parameters and other influencing factors are regulated properly and precisely. However, in sandblasting, process parameters and other influencing factors are not regulated precisely. After that, in abrasive jet machining, quality and finish of the machined surface achieved by abrasive jet machining are comparatively better. But in sandblasting, quality and finish of the machined surface are not so good. Next, it's costlier for abrasive jet machining to be used but precise, thus beneficial for industrial high-quality finishing requirements. Sandblasting is cheaper and thus efficient for common civil works. Then, abrasive jet machining is usually used for removal of coating and rust, and it's also used to cut profiles or drill holes on hard metals, but sandblasting is mainly used to remove rust and coating from solid surfaces. Finally, abrasive jet machining is usually carried out in rooms with proper ventilation, thus it's less hazardous, while sandblasting is often carried out in open atmospheres, thus it causes air pollution. Workers are also exposed to various occupational lung diseases such as silicosis. Now let's discover another mechanical non-traditional machining process, the ultrasonic machining. In ultrasonic machining, a tool is made to vibrate at ultrasonic frequency of 20 to 30 kHz with abrasive slurry. The vibration of the tool and abrasive slurry removes material in form of small grains. Both abrasive jet machining and ultrasonic machining are mechanical energy-based processes where material is removed by impact erosion. In abrasive jet machining, hard abrasive particles are mixed with highly pressurized air at a predefined mixing ratio, and the mixture is then allowed to come out via a nozzle in form of narrow jet. Regarding the differences, in abrasive jet machining, a very high velocity between 100 and 300 meters per second jet of air abrasive mixture is utilized for machining purpose. In ultrasound machining, a high frequency, more than 20 kHz but low amplitude, less than 0.1 mm vibration is utilized for machining purpose. In abrasive jet machining, the high velocity jet is allowed to directly strike the workpiece, but in ultrasound machining, the vibration is not directly imparted to the workpiece. Instead, vibration is imparted on an abrasive slurry that flows through a narrow gap between a shaped tool and workpiece. Next, in abrasive jet machining, it doesn't require any specialized tool. Intended profile can be cut by moving the work table and rotating the nozzle if required, but in ultrasound machining, it is mandatorily requires a physical tool having inverse profile of the intended shape. Accordingly, shape of the machined feature relies on tool profile. After that, abrasive jet machining requires an air compressor cum dryer to deliver highly pressurized clean air. This air is then mixed with abrasive. The pressure energy is converted into kinetic energy by the nozzle, and thus high velocity jet is obtained. In ultrasound machining, it doesn't require any compressor unit. Instead, it requires a magnetostrictive transducer to generate vibration and a horn to deliver vibration at intended amplitude. The tool is mounted at the tip of a horn. Abrasive jet machining offers comparatively higher material removal rate in the order of 5 to 10 centimeters cubed per second, but ultrasound machining provides very low material removal rate, and which is typically around 0.005 centimeter cubes per second. Then abrasive jet machining can be used for ductile and brittle materials. However, it's preferred for hard, brittle materials due to the risk of abrasive embedment in soft materials. Ultrasound machining is commonly used for machining brittle materials, especially those which are electrically non-conductive like glass, ceramic, carbide, etc. Finally, abrasive jet machining produces extreme noise during operation. Abrasive grits are sometimes scattered out of the chamber, so proper protection is mandatory for the worker. In ultrasound machining, it's relatively safe in this scenario. Thank you for watching, and see you in the third part and last part of the lecture Non-Traditional Machining Processes. See you next time!